Hi students, now in this video lecture we will be introduced to colligative properties, right? So colligative properties are those properties of dilute solutions that depend only upon the number of solute particles, right? And it does not depend upon the nature of solute particles, right? Only upon the number of solute particles, right? For example, like we have studied previously that when we added solute, right, to a pure solvent, it resulted into the lowering of vapor pressure, right? And it is due to the number of solute particles that resulted into the vapor pressure being lowered. Vapor pressure went down due to the number of solute particles, right? And we have also studied, as per Raoult's law, that the vapor pressure of solution, if you look at this relation, the vapor pressure of solution is directly proportional to the mole fraction of solvent, right? And if we increase the solute particles, right, that would result into the less mole fraction of solvent, right? If we are adding more solute, that means the mole fraction of solvent will go down, and if the mole fraction of solvent will go down by the addition of more solute particles, that would result into the further lowering of vapor pressure, right? If you look at this, so these kind of properties that depend on the number of solute particles are known as colligative properties, right? And since the lowering of vapor pressure has also resulted in the elevation of boiling point, like we have studied in the previous lecture, and it has also resulted into depression of freezing point, right? So all these properties, right, lowering of vapor pressure, elevation of boiling point, depression of freezing point, right? And there is also another one, osmotic pressure, which we have not been introduced, right? We'll do it in future lecture. So all these properties are colligative properties, right? Because these properties vary based on the number of solute particles, right? And all these properties, colligative means linked together. All these colligative properties we have just discussed are linked to one another, right? Because elevation in boiling point is related to lowering of vapor pressure. Similarly, depression in freezing point is also related to the number of solute particles in solvent, or number of solute particles in solution, right? So now in this video lecture, using this small derivation, we will prove that the colligative property, which is relative lowering of vapor pressure, we will do the first colligative property, the relative lowering of vapor pressure, in detail in this lecture. So we'll prove that the relative lowering of vapor pressure depends directly on the number of solute particles, right? Now in the previous lecture, we have already understood how the addition of solute resulted into the lowering of vapor pressure, because when we added solute, these red dots show solute molecules, and green circles, these green dots show solvent molecules. So when we added solute to this pure solvent, the number of solvent molecules at the surface were replaced by these solute molecules, right, which resulted into less number of solvent molecules escaping into vapor phase. So that means the rate of evaporation has decreased, right? So less number of solvent molecules are going into vapor phase, which has resulted into lowering of vapor pressure, right? So this is the diagram that we have already done. Vapor due to solvent, right? And vapor above this solution is only due to solvent, because solute, as we know, as non-volatile. So as per Raoult's law, we have already proved that vapor pressure of solution is equal to the product of vapor pressure of pure solvent and the mole fraction of solvent. X1 is the mole fraction of solvent. Suppose this is a solution that consists of N1 moles of solute, right, and N1 moles of solvent, right? And X1 is the mole fraction of solvent and X2 is the mole fraction of solute, right? And by definition, mole fraction is the ratio of the number of moles of one component to the total number of moles of all the components in solution, right? So x1 would be n1, which is the total, which is the number of moles of solvent divided by total moles in solution, which is due to solute and solvent, n1 plus n2. Similarly, mole fraction of solute would be ratio of moles of solute divided by the total number of total moles of solute and solvent, right, in the solution. So these are mole fractions which we would be using in derivation. So when we added solute, it resulted into lowering of vapor pressure. Lowering of vapor pressure due to addition of non-volatile solute, right, is P0 minus P, right? P0 is the vapor pressure of pure solvent, right, which is high as compared to this solution, because addition of solute resulted into lowering of vapor pressure. So lowering of vapor pressure would be P0 minus P. P is the vapor pressure of this solvent, which is less than P0, right? And we know that now delta P is P0 minus, we just put the value of P from this Raoult's law expression. So P0 minus P0 x1, right? P is common, 1 minus x1, right? And we know that x1, that the addition of x1 plus x2 mole fraction, the sum of all mole fractions is 1, is not more than unity. So x1 plus x2 is equals to 1, right? So if we replace 1 minus x with x2, right, this 1 minus x, right, can be replaced with x2. So value of 1 minus x is x2. It's from here. If you take it over here, x2 is equals to 1 minus x1, right? So we'll put the value of 1 minus x from here. It's P0 x2, right? And if we divide, in this step we have divided both sides with P0, right? So delta P, which is lowering of vapor pressure, divided by P0, and P0 cancels out. So this is x2. x2 is the mole fraction of solute. So delta P upon P0, right, this delta P upon P0, this is lowering of vapor pressure compared to the vapor pressure of pure solvent, right? So this expression is known as relative lowering of vapor pressure. Lowering of vapor pressure relative to that of pure solvent, right, which is, as we have calculated, is equal to the mole fraction of solute, right? So P0, we'll just put the values. P0 is what? Delta P is what? Delta P is P minus P upon P0, right? And this is equal to x2. So P0 minus P, right, upon P0, this is relative lowering of vapor pressure, right? So if we just substitute the value of x2, which is mole fraction of solute, from here, it would be n2 upon n1 plus n2, right? So this relative lowering of vapor pressure is equal to the mole fraction of, from this expression we got to know that relative lowering of vapor pressure is equal to the mole fraction of solute, right, which has proved us that lowering of vapor pressure is a colligative property, because it depends on the number of solute particles. It depends on the mole fraction of solute, right? So this proves that relative lowering of vapor pressure is a colligative property. Now let's just see a little more. So P0 upon this delta P upon P0 is relative lowering of vapor pressure, which is equal to the mole fraction of solute in solvent. This is another form of Raoult's law, right? So this, now since N1 is, till this point we have proved that relative lowering of vapor pressure is equal to, or it directly depends on, the solute, mole fraction of solute, right? So this is a colligative property. Now let's work it a little more. Now this is equal to x2, which is the mole fraction of solute. Now in dilute solution, we know that N1 is number of moles of solvent and N2 is number of moles of solute, right? So in a dilute solution, this in a dilute solution, this P0, right, this P0 and N1, this represents the vapor pressure of pure solvent, and this is moles of the solvent. And in dilute solution, we know that this is N1 is moles of number of moles of solvent, right? And in dilute solution, this N1 is greater than N2, right? N1 is very much greater than N2. This N1 is very much greater than N2, right? So N2 is negligible as compared to N1, right? So we'll replace it, right? We'll replace this quantity with N1 because N2 is negligible since N1 is very much greater than N2. So this N2 is negligible. So we can write this expression as P0 minus P upon P0 equal to N2 upon N1, right? So this N2 upon N1, we have ignored N2 over here, right? So now for a definite quantity of solvent, P0 and X1 are constant. If we are taking a definite quantity of solvent, this P0, that is vapor pressure of the pure solvent, and this N1, that is the moles of solvent, are constant. So we can write it as P0 minus P is equals to N2, right? Or P0 minus P is directly proportional to N2, and we know that P0 minus P is nothing but relative is lowering of vapor pressure, right? So lowering of vapor pressure is directly proportional to N2. N2 is number of moles of solute, right? N2 is number of moles of solute particles. So we proved that lowering of vapor pressure or relative lowering of vapor pressure directly depends on the number of moles of solute particles based on this relation. So this proves that it is a colligative property, since colligative property depends on the number of solute particles. So this proves that this delta P, which is lowering of vapor pressure or relative lowering of vapor pressure, since P0 was constant, so we have removed it, but this is in actual, this is relative lowering of vapor pressure, which directly depends on N2, which is the number of moles of solute particles, right? So this is a colligative property. We have proved it, right? So relative lowering of vapor pressure of a solvent is proportional to the number of moles of solute only, and is independent of the nature of solute. Hence lowering of vapor pressure is a colligative property, right? This we have proved. So this is very important. Just go through this, right? And I hope all this is clear to you. Thanks.